Hey guys, and welcome to part 2 of our gases unit. And today, our big theme is going to be pressure. So we're talking about pressure today. And we're going to kick things off with just a little video about well, you might have heard of this before, but let's just fire it up. Take a look. Perfect. Good start. So, kid gets vacuumed into a bag. Bag sucks him in there. He can't move. He's stuck. He has to tell someone else to stop before he can't do anything. So, question. What is keeping this person immobilized? Why is it they can't move just because the air is out of the bag, right? It's just what's holding them there. So if you think about it, we haven't added anything to the person, right? There's nothing holding them in place. He's not tied down. All we've done is remove air. And so what's keeping the person pinned in place is the pressure of the weight of the air around him. With no air in the bag, we've created a vacuum, and so atmospheric pressure has pinned that person into a bag. And so what is pressure? Well, it's just the weight of the air that pushes on you. So here's the earth. Here's you. Happy person standing on the earth. If you were to take a ginormous glass column, all the way up to the edge of space there, that column is filled with air, right? And we know that air doesn't weigh that much, but when you have, 80 some kilometers, 80 plus, I think it's almost 100 kilometers to the edge of space. I don't know the exact number, but you got at least 80 kilometers of air above you. That air is being pulled down by gravity, right? And so it's going to exert some pressure on you. You don't feel it because you're used to it. It's normal for us, but there is a ton of air pressure on us. And when you suck all the air out of the bag, you've removed the air pressure from all other directions because air pushes in all directions. It doesn't just push down. If I have a box filled with air, those air molecules are bouncing all over the place. And so they put pressure on every side of that container. So you're standing here, sitting here, reading, listening to this video. The air is bouncing off the bottoms of your hands, the tops of your hands, the bottoms of your arms, the tops of your hands. It's pushing at you from all directions. If you were to remove all of the air from immediately around your body, for example, by using a vacuum to suck it all out, then you're only getting pushed inwards. So we had the guy sitting there. I don't even want to try and draw that. It would be too bad. But the air is pushing in on him and forcing his arms and legs in towards his body because there's no air pressure in the opposite direction. That's just the pressure the air puts on us every day, but it's not being counterbalanced. And so we measure that push. We measure pressure by looking at how much force is applied over an area. So how much force is applied over an area? So if I had a spot this big on the ground, how much force is pushing down on that? So if this spot was like 1 meter squared, and let's say it was 10 newtons, in total, I would say, okay, the pressure is 10 newtons per meter squared. So it's pressure over some area. So you can use any area you want, any unit of force you want. You can do weight, you can do kilograms, you can do newtons, you can do something else, but it's just how much force is applied. All right, stop. Do not write this next section. So you've been warned. The next section is going to be a history of pressure. You don't need to write this down. It's an information thing. It's going to take a little while, so don't kill all your ink. So, brief history of pressure. Starts with Galileo, kind of famous guy, Galileo Galilei. He's believed to have been one of the first to suggest in any kind of experiment, really, to test the relationship between density of a liquid and the height you can pump it. So you can't just pump water up as far as you want. You can't just run a pump and have water go all the way to space. There's a limit to this based on how dense the liquid is. And so this happens back in 1640. So we're like in the mid-1600s here. Galileo conducts this suction pump experiment at a well, together with two assistants, Evangelista Torricelli, who we're going to talk about in a minute because he's super famous, and Giovanni Baliani. So he lowers this really long tube way down into the well, and he drapes it up over a wooden crossbeam 3 meters above the well's edge. Let's draw this. I could do this. So here's our well. We've got a wood beam, and so we have a pipe that is U-shaped that goes up and over and way down to the bottom of the well. There, long tube, all the way down. And so this U shape, they hook up to a pump. It's got a little crank on it. It's a hand pump. Here's Torricelli, his assistant. Fantastic. So his assistants pump this wooden handle. They slowly suck the air out of this tube, and they pull water higher and higher and higher up the tube, as high as they can go. And they keep pumping until the tube flattens itself out, like a run-over drinking straw, just sucked flat. And so Galileo noticed that no matter how hard they worked, no matter what kind of pipe they used, no matter how they set it up, the water never went higher than 9.7 meters above the water level. So wherever the well's water level is, wherever they started pumping from, he could never get the water to go to 10 meters. Wouldn't happen. 9.7 was always the cap. It was the same in every test, no matter how he set it up. If he tried to evacuate and suck all the air out of that tube, water would get sucked up, but only to 9.7 meters. He's like, okay, why is it exactly this number? And so he theorizes that there's some connection between the suction he's creating and how high water can go. And so in the early 1600s, he'd argued that suction pumps were able to draw water from a well because of the vacuum inside the pump. So he said the vacuum creates a force, and it has enough force to pull the water up a certain amount. That'll change based on your liquid. Now, Galileo was wrong, and after he died, the Italian mathematician and physicist, and also his famous lab assistant, Evangelista Torricelli, proposed another explanation. He suggested that the air in our atmosphere has weight, and so that it's not the vacuum that's pushing water or pulling water up, it's actually the weight of the atmosphere pushing down on the well that forces water up the tube, because there's no more air in there to push back on it. Do I have a drawing of this? Yeah, here it is. So just look at this drawing real quick. We're going to go back. So it's not the suction up here that causes water to go up. It's the fact that I'm pushing down super hard with atmospheric pressure all over this liquid. And so where does it have to go? Well, the pressure pushes that liquid up the tube. So that was his theory. That's kind of what it looked like. So in 1646, and then this is 1 year before his death, so obviously he had a bad day shortly after this, but in 1646, he described an experiment in which a glass tube about 1 meter long was sealed at one end. So you've got like a test tube. Picture a test tube. You fill that test tube to the top with mercury. Then you turn it upside down very carefully, because you don't want to touch mercury, and you stick it into a dish, which is also filled with mercury. So you'd have your test tube filled to the top with mercury, sitting in a dish, also filled with mercury. And then you let go of the test tube. And what he noticed was some, but not all of the mercury drained out. So a little gap formed at the top of the test tube as some mercury drained, but the whole thing didn't empty. There was a bunch of mercury left in the tube. And so Torricelli explained this by assuming that mercury drains from the glass tube. So he's basically disproving the force of vacuum theory. He's like, look, there's no suction here. There's no pump. There's nothing here that should be holding this mercury up, so it should fall, according to Galileo. So Torricelli explained this by assuming that mercury must drain from the glass tube until the force of the mercury pushing down on the inside of the tube, so that force pushing down, matches the force of the atmosphere pushing down. Once the atmosphere balances the inside weight of that mercury, everything is balanced and the liquid will stop draining. Which leads us back to this diagram here, gives you another explanation for it. So Torricelli predicted the height of the mercury column should change from day to day as the pressure of the atmosphere changed. And so today, this exact apparatus is known as a barometer. And we use it to measure atmospheric pressure. They still use the same kind of idea to measure atmospheric pressure. And baro, for barometer, is from the Greek word baros, meaning weight, because it literally measures the weight of the atmosphere. That giant glass column of air, how much air is weighing down on that mercury. So that's why they call it a barometer. Now, repeated experiments, they did this over and over and over again, they did this all over the place. They figured out the average pressure of the atmosphere At sea level, because, the higher you go above sea level, the less atmosphere there is above you, right? So you have less pressure. So the average pressure of the atmosphere at sea level is equal to the pressure of a column of mercury 760 millimeters tall. And so now we have invented a standard unit of pressure known as the atmosphere. So one Earth atmosphere of pressure should be 760 millimeters of mercury. And as weird as it sounds, millimeters mercury is still a unit of pressure we use today. Next comes a guy named Otto von Guericke. Now, he invented the first air pump in 1650 and used it to study vacuums. And his studies revealed light travels through a vacuum, but sound does not. And everyone's like, oh, mind blown. And then in 1654, at a famous series of experiments that were performed before Emperor Ferdinand III at Regensburg, Guericke placed 2 copper bowls. So he grabs a copper bowl. Here's a copper bowl. He grabs another copper bowl. There's the other copper bowl. So he puts these 2 copper bowls together to form a hollow sphere, about 14 inches in diameter. And he hooked up a little valve to one side and sucked all the air out. And now he attached a handle to each of these bowls as well. And so he sucked the air out of the handle. He's like, here, 2 copper bowls. All I've done is take the air out. Here, pull these bowls apart. And he hooked up literally plow horses, big, strong horses. And the horses couldn't even pull the bowls apart, even though they were held together only by the air pressure of the atmosphere pushing on the bowl. Because there's nothing left inside to push against it, our atmospheric pressure pins those bowls together. And that crazy amount of force that air pressure actually exerts, that's kind of the first demonstration of how strong that force can be. And so you see we got this drawing here of the 2 horses trying to pull these giant bowls apart right in the middle. So it's a very famous experiment. I've got a couple mini Magdeburg hemispheres, and so we're going to take a look at some of that probably next class, and we'll see, play around a bit with the Magdeburg spheres, see what we can do. Next on our list was Blaise Pascal. Now, according to Blaise Pascal's law, 1653, any force that you apply to a confined fluid is transmitted uniformly in all directions through the fluid. So if I have a tube like this, and it is totally filled with liquid, top to bottom, and let's say I have a plunger on this side. If I push that plunger down, let's say I put 10 newtons of force down there, that 10 newtons of force, let's say it's 10 newtons per meter squared. So I've pushed down at 10 newtons per meter squared. That 10 newtons per meter squared of force goes through the entire system. At every single point in this liquid, you would have 10 newtons per meter squared pushing at the same time. Now, this is kind of crazy for 2 reasons. One, it becomes fundamental in the creation of hydraulic systems. I can create a little reservoir of liquid, and then I can run a line as far as I want to somewhere else with another little reservoir. And let's say this has a piston at one end, and I've got a piston at this end. If I push this piston down, that force goes through the entire liquid instantaneously and would push this piston out. And the other really crazy thing about this is if I have a tiny reservoir and it leads to a large reservoir. So this one has a massive plunger. This one has a tiny plunger. If I push down on this tiny plunger with 10 newtons per meter squared, so let's just say that this tiny plunger was a meter squared. So it's actually a pretty big plunger. Well, how big would this one be? Let's say 1, 2, 3, 4, 5, 6. Let's say that this one is 7 meters squared. So I push down here at 10 newtons per meter squared. Guess how much force this now has? 10 times 7. This is now at 70. This is now pushing up with 70 newtons of force. Basically, this means if I have a tiny little plunger in front of me, I can lift a car with this very easily. Now, it sounds like this is breaking all kinds of laws of conservation of like energy and physics and motion and stuff. But here's the trade-off. This tiny plunger, I would have to move down a couple like if I move that plunger down 7 meters, I would only move this one up 1 meter. So I get a lot more force, but I get a lot less distance. So that's kind of the trade-off of hydraulic systems. But we still use that today. Next up, Christian Huygens? Question mark? Invented the manometer in 1661. Now, I'm going to flip to the next slide in a second to show you guys what a manometer is, but it's a very handy way to measure the difference in pressure between two gases. And so versions of this are still used today. So they call this an open manometer. So you put a little liquid in a U-shaped tube, boom, you're done. That's it. If the pressure is equal on both sides, well, then the level of the liquid is the same, right? But let's say I hook up a hose to this side and stick it inside an air duct. So here's my air duct over here. It's carrying air through the building. If that air duct has higher than atmospheric pressure, it'll push the liquid down on this side and up on this side. You end up with a drawing that looks like this. I'd have high pressure pushing it down. On the flip side, if I had a low pressure system in that duct, then the pressure of the atmosphere would be bigger, so I'd end up with extra liquid on this side and less liquid on this side. And by measuring the difference between where the liquid is, you can tell what the actual pressure is. Like, I know where atmospheric pressure was supposed to be, so this is where atmosphere is, this is where I'm actually at. By measuring the difference, you can, if depending on the liquid you're using, you can calculate what the actual pressure difference is between two areas. And you can find the exact pressure because you can compare it to the atmosphere. So a very handy little device for figuring out pressures if you're doing stuff like if you're looking at hydraulic systems or you're looking at like heating and ventilating systems. You can tell how much pressure is in a duct really quickly with just a little glass tube. So after the manometer, John Dalton followed, and this is 1871. It's a couple hundred years here. People are like, all right, I think we're good with pressure. But John Dalton came along, and this was after a bunch of atomic theory was done. You might even remember John Dalton was one of the guys who made up an atomic theory. He stated that the total pressure of a mixture of gases is equal to the sum of the partial pressures of the individual component gases. Okay, so let's translate this a little bit into English. I've got a balloon. Oh, not a balloon. I want something a little more rigid than that. I got a box, and it's filled with nitrogen and oxygen. Let's say it is 60% nitrogen, 40% oxygen. Cool. If I want to know how much pressure is in that box, I would have to know if I had a box that was that had the same amount of nitrogen. So whatever 60, if it was like, I don't know, 10 liters, let's say 60% was 10 liters. So if I had 10 liters of nitrogen in the same shape box, and I had, I don't know, let's say this was 6 liters of oxygen. I don't know what the actual percentage would go to in this box. So these boxes are the same size. Whatever the pressure is that nitrogen puts out, plus the pressure that oxygen puts out, equals the pressure that the two of them put out when combined in the same box. So that was Dalton's law. And it seems like, oh, that kind of makes sense. If they had no concept that putting gases together would actually work together, or if they would, maybe the gases dissolve together and exert the higher one's pressure. We had no idea. So Dalton came along at the time and figured the partial pressure is the pressure that each gas would exert if it alone occupied the full volume of the box. And then he did a bunch of experiments and figured out that whatever this partial pressure is and this partial pressure is, by adding those together, you get the total pressure. So that was kind of a big thing in pressure theory at the time. Pass our manometers here. And now, this is something you guys probably know. We know now that if the temperature of a sample of gas is increased, if I heat up a gas, the pressure of the gas increases as well, right? You don't want to throw compressed gas cylinders on a fire because they get really pressurized and then explode. That'd be bad. And the reverse is true. If you cool gases down, they tend to get smaller. Like, take a basketball outside at -40, the ball gets flat, right? As you cool it off, the gas inside the basketball decreases the pressure. Now, the increase, when you heat things up, the increase in kinetic energy results in the molecules, if we're talking molecular theory, the molecules of gas hit the walls of the container with more force because they're moving faster. So the faster they move, the more force they have. The more force they have, we measure that as pressure. So fast-moving particles hit walls more frequently and harder, and we feel more pressure. Now, the guy who figured this out was a French chemist, Joseph Gay-Lussac. So he was again in like early 18 to mid 1800s there. And he discovered the relationship. He's the guy that discovered this between pressure and its absolute temperature. And so he has the law named after him. Gay-Lussac's law states that the pressure of a the pressure of a given mass varies directly with the temperature of the gas. Now, this is if your volume is kept constant. You can't change the size of the container, of course, that messes up things. But if you've got the same size container, you're in a ball, and that ball doesn't change volume, then temperature will directly affect your pressure. So that's a brief history of some pressure stuff that we might end up talking about a bit later. So, okay, now we're going to write again. That was our history. Let's get some interesting things. Well, not interesting. That was really interesting, but stuff we can use math-wise. So let's look first at how do we measure pressure. So we saw a few examples there. We saw newtons of force per square meter. That's what I was using. And because newtons are kind of our standard for force, and square meters are our standard for area, you put those together and you call 1 Newton per square meter a Pascal. So when I was talking about 10 newtons per square meter, I had 10 pascals of pressure. Now, a Pascal, 1 Newton, is a very small amount. And if you take a very small amount and spread it out over a square meter, well, that's minuscule. You barely feel what a Pascal pressure would be. I don't think you'd even notice it. And so because they're so very small, we usually use kilopascals instead, or kPa. So if you've ever filled up a tire or something, sometimes they'll have the measurements on them. And how many kPa of pressure do you have to fill this tire with? The second common measurement, as we talked about, still used today, millimeters mercury. Scientists often will measure pressure differences using a manometer, just filled with mercury. So that U-shaped tube, stuffed with mercury, off you go. The distance between the mercury levels tells you the pressure difference. Now, why mercury? Because it is really dense, which means it doesn't move much in response to pressures, which means it's not going to shoot up and out the other end of the tube. If you do something like water, which isn't very dense, you would need a massive glass tube to actually measure decent differences. So mercury doesn't move as much because it's so dense, which makes it ideal for measuring bigger temperature differences, or pressure differences, Last one we talked about already was atmospheres. So 1 atmosphere is how much pressure our actual Earth atmosphere puts on you. So 760 millimeters of mercury, we'd call that an atmosphere. So you can measure pressure as oh yeah, that's 5 atmospheres of pressure, or that's a half an atmosphere of pressure. We've reduced the pressure a bit. So these are common ways that we can measure. And if you can measure in multiple ways, of course, you need to be able to convert between pressures. And so to convert between pressures, you just need to know how they relate. 1 atmosphere is 760 millimeters mercury. We knew that already. It is also equal to 101.3 kilopascals, kPa, or 1,000 millibar, which is another unit of pressure, which we didn't really talk about the history of, but it's not as common. But it's around. Just be aware. There's things called bar. You can convert it. 1,000 bar is millibar, is an atmosphere. So let's do an example. I have 2 atmospheres, so I'm going to write down what I know. I need to get out of atmospheres, and I need to get into kilopascals. So what is my relationship here between kilopascals and atmospheres? Well, let's change my color. I know that 1 atmosphere is 101.3 kPa. And so that will be my conversion factor. I just have to do this the same way I was doing the mole conversions last unit. I grab 2 atmospheres, I times it by 101.3, and it turns out that 2 atmospheres is 202.6 kilopascals. That's not too bad, right? Let's try another one. What is 1,750 millimeters of mercury? And I need to get out of millimeters mercury. I need to get in to atmospheres. Okay. What's my relationship? 1 atmosphere is 760. So 1 atmosphere is 760 millimeters mercury. So I take my 1750 times 1, but you don't need to do it because it's times 1, divide by 760. Turns out if I had 1750 millimeters mercury, I would have 2.3 atmospheres of pressure. So that kind of sums up our intro to pressure here. We're going to be working with that a little bit and get a chance to play around with it next time I see you guys. But until then, have a great night, and I'll talk to you later.